Hey everyone, just wanted to give a quick review of vascular resistance that we looked at this morning in class. This is an example from what we have in the book, and when the blood pressure decreases, we need to get the blood pressure back up. So a response of the vascular system is to constrict, and when you constrict, the blood pressure inside the lumen will increase because you're squeezing the blood that's inside the vessel. So pressures will go up. So when blood pressure is down, the medulla oblongata is responsible for increasing its sympathetic nerve activity to the vessels, and the vessels will vasoconstrict. If the blood pressure is elevated and we need to lower the pressure, the medulla oblongata decreases its sympathetic nerve activity, which causes the vessels to dilate. We then looked at another picture in your book that looked like this. Make sure I have that in the frame, where we have the body of the heart itself, the aorta, the aortic arch, and then we have our left and our right carotid arteries that rise high into the neck, and then we see a large area where baroreceptors are located immediately before that carotid artery bifurcates into the internal and external carotid arteries. And then we also have pressure receptors or baroreceptors in the arch of the aorta itself. The pathway by which the carotid baroreceptors travel is along the 9th cranial nerve, which is also known as the glossopharyngeal nerve. The aortic baroreceptors or the pressure receptors travel via the 10th cranial nerve, which is the vagus nerve. I asked you guys to remember these because we're going to talk about them every now and then. When the pressure is very high in the system, the pressure receptors stretch, they bulge. When the pressure is very low, they return back to their normal shape and then become smaller. So when pressure is decreased, that action tells the baroreceptors that the pressure is low. So when the pressure is low, the impulses that are sent from the baroreceptors to the medulla oblongata decrease. When the medulla oblongata senses that its impulses being received have decreased along that afferent pathway, it knows blood pressure is going down. When it understands blood pressure is going down, the medulla oblongata increases sympathetic activity, just like we saw here. And with the increase in sympathetic nerve activity, we see the vessels vasoconstrict, the heart rate goes up, the contractile force goes up, cardiac output increases, so blood pressure goes back up. Blood pressure is restored. Alright. Then we finished it off by actually calculating vascular resistance, quantifying it numerically. So I drew the hemodynamic loop for you, and this is just a review, but you see the normal pressures in the pulmonary artery. We have a mean of 15. Pulmonary vein, 8 torr. Your systemic arterial system, 93, which is the mean arterial pressure. We have a central venous pressure of 4. So all these numbers should look very familiar. Cardiac output of 5. And I just have reminded us that we have cardiac output going through the pulmonary circulation. We have cardiac output going through the systemic circulation. And to calculate vascular resistance, you simply take the change in pressure, the delta P, in the numerator, and then find the change in flow, which is going to be our cardiac output, and you plug that into the denominator. Right? So we'll first solve for pulmonary vascular resistance, which is PVR. That's going to equal the drive pressure, which is your mean of 15 on the high end, and then subtract on the low end the 8. So we're going to determine the delta P. Flow on the bottom in the denominator, 5 liters per minute. Simple as that. When you solve, you'll see 7 torr over 5 liters per minute. I think the math that gave us in class today was 1.4 torr. I'm just going to write this out as millimeters per mercury because that's how you usually see it expressed, per liter per minute. Pretty easy calculation. Alright, for systemic vascular resistance, which is called SVR, you have to find your delta P, which is your high pressure. The highest is 93 average. right, minus the low pressure, which is our CVP, 4 torr. Again, divide by cardiac output because that's your flow. All right, that gave us 89 torr over 5 liters a minute. I forget what that math is, so I'm going to do that on my calculator. 17.8 millimeters of mercury per liter per minute. So please know how to do the calculation, know how to perform it. What we'll talk about later subsequently will be how changes within the hemodynamic loop will cause changes in vascular resistance. All right, thank you.